Hello everyone. Today's in this lecture, I'm going to demonstrate how to apply method of separation of variables to solve partial differential equations. So before solving actual problems, let me give the working rule. So how to go about this method. So suppose let us consider the given PDE is of this form. So given PD is of this form. So here f of x comma y comma u ux and so on is equal to 0. Then in the first step you assume the solution of this PDA as u of x comma y is equal to x of x and y of y is equal to x into y. So why we are assuming like this is u is a function of two variables here. So u is a dependent variable which is a function of two variables x and y. So here we are decomposing this solution u into product of two functions. One is capital X, which is a function of only small x, and the other one is capital Y, which is a function of only small y. So we decompose this solution u of xy as a product of two single valued functions, capital X and capital Y. So that for simplicity I have written it as u is equal to xy. Then in the next step you substitute this u is equal to xy in a given PDE and replace this partial derivatives dou u by dou x by y times d capital X by d small x. Why it is d times why this partial derivative becomes dx by d small x is because capital X is only function of small x. So therefore the partial derivative becomes ordinary derivative. Similarly, dou u by dou y is equal to capital X times du by dy, and dou square u by dou x square is capital Y times d square capital X by d small x square, and so on. So replace this partial derivatives by ordinary derivatives as given in this step 2. So then again in the step 3, separate these variables further. That means you bring all capital X terms one side and capital Y terms other side. So by doing this, in the next step we'll get something like it is a function of x, one side is completely function of x, other side is completely function of y. So these two are equal. Generally this equality is not holds good, because this equality is not valid unless until both left hand side and right hand side take same values. So let's say that value is equal to k, this k being in a some arbitrary constant. This k is a some arbitrary constant, so that these two left hand side, that is f of x, is equal to g of y is equal to k. So individually we can take f of x is equal to k and g of y is equal to k. So hence this step 4 will give rise to the system of ODEs, because in the step 2 we replaced all partial derivatives by ordinary derivatives. Hence this method of separation of variables reduce a partial differential equation into system of ODEs. Now in the next step you solve this ODE separately for capital X and separately for capital Y, and then substitute back in step 1, that is u is equal to xy. Thereby we get the complete solution. Suppose if any conditions are given, like initial or boundary conditions, that you can substitute and find the respective constants you will get while solving the system of ODEs. So this is the procedure for the method of separation of variables. Now let me demonstrate this with respect to this example. So let us consider example is solve this example. Solve dou u by dou x plus dou u by dou y is equal to u by using method of separation of variables. So here very important note that there is no condition is given. So and further you observe here. So u is differentiated partially with respect to x in first term. So here, and u is differentiated partially with respect to y in the second term, and that is equal to u. Now as I mentioned in the working rule, the first step is you observe u is a function of xy. So you decompose u of xy as a product of capital X and capital Y, and capital X is function of x only, capital Y is function of y only. Then substitute this in the given PDE. You substitute in this in the given PDE here. Then we'll get dou by dou x of u is x into y plus dou by dou y of u is x into y is equal to right hand side u is xy. So we get this step. So here you observe that in the first term, so it is a partial derivative with respect to x. So y is just like it is like a constant, so that you can take outside the derivative. So therefore the first term becomes y into, then remaining is dou by dou x of capital X, but capital X is function of only small x. Hence we can replace this partial derivative by just ordinary derivative, so that you can write it as d capital X by d small x. Similarly, second term x is constant, that you can take outside. So dou y by dou small y is just d capital Y by d small y is equal to right hand side, it is x into y. So this x and y are for function of only single variables. So partial derivatives becomes ordinary derivatives. That is the very important takeaway from this method. Then further, to separate the capital X terms one side and capital Y terms on other side, just divide throughout by x into y, that is u. So then we'll get in the first term in this step, so y by xy, so y get cancelled, we'll get 1 by x d capital X by d small x, plus similarly in the second term, so x by xy, so x get cancels, we remain with 1 by y d capital Y by d small y, that is equal to, so right hand side xy by xy, that is 1. So we we get in the next step, we get it is a differential equation something like this: 1 by x d capital X by d small x plus 1 by y d capital Y by d small y is equal to 1. So in the next step, you bring all capital X terms one side and capital Y terms other side. So for that purpose, I have taken here 1 with this right hand side is a constant that you can combine with either capital Y or capital X, does not matter. But in this problem, I have taken 1 to left hand side and 1 by y, 1 by capital Y, d capital Y by d small y to right hand side. So I brought all capital X terms one side and capital Y terms one side. So like this. So 1 by x d capital X by d small x minus 1 is equal to minus 1 by y d capital Y by d small y. So now you check that this is left hand side is a function of x and right hand side is a function of y. So these two are equal. It is something like x is equal to y. We know that x is equal to y is possible only if x takes if x is equal to 5, then y must be 5. So x and y must take same values. So therefore this inequality holds only if this f of x is equal to g of y is equal to k. Hence this equalities we can take this both are equal to same value. Let's say k is some arbitrary number. Hence we can take this left hand side is equal to that k. So 1 by x d capital X by d small x minus 1 is equal to k, and minus 1 by y d capital Y by d small y is equal to k. So therefore this will reduce to, so the system of ODEs like this: 1 by x d capital X by d small x minus 1 is equal to k, and minus 1 by y d capital Y by d small y is equal to k. So this is the system of ODEs. Now in the next step, you solve these two equations separately, find what is capital X, capital Y, and substitute back in u. That will give the required solution. So solve this ODEs individually, substitute in this u. So first let us consider first ODE: 1 by x dx by d small x minus 1 is equal to k. Again I'll use the separation of variables. So that means I bring small x terms one side, capital X terms other side. So this we can rearrange it as d capital X by capital X is equal to k plus 1 into d small x. So this is just a first order differential equation. Integrating on both sides will get the required solution. That is, integration of dx by x is log x is equal to k plus 1 into x plus some constant of integration that I have written it as log a. Then rearrange this, take log to other side and rearrange the terms, will get final solution for x as x is equal to 8 times e power k plus 1 into x. So this is solution for first ODE. Similarly, take second ODE, that is minus 1 by y dy by d small y is equal to k. And again separate the small y terms and capital Y terms on left and right hand sides. So we get d capital Y by capital Y is equal to minus k times dy. So this is again a first order differential equation. You just integrate on both sides, will get the required solution. So integration of dy by y is log y minus k times dy integration is y plus some constant of integration. I've written it as log b. So then take log to other side and rearrange the terms. We'll get y is equal to b into e power minus ky. This is a solution for the second ODE. Now you substitute this y and x. Substitute this y and x in u is equal to xy, and rearrange the terms. We'll get the final solution for this is c times e power k plus 1 into x minus ky is the complete solution. This is the solution of the given PD. I hope that that makes sense and it is clear. So we'll move on to the next example. So then in the next example, I've considered as solve dou u by dou x is equal to 2 times dou u by dou t plus u, subject to the condition u of x comma 0 is 6 times e power minus 3x. So here I've taken a problem with condition. This is called initial condition because at t equal to 0, this is the solution. So now, as we discussed in the previous problem, also in the working rule, first step is you identify which is the dependent variable and independent variables. You check u differentiated partially, so with respect to x, so u is dependent, x is independent. U differentiated partially with respect to t, so therefore u is dependent, t is independent. So therefore u is a function of x and t, and hence we can assume that solution u of x comma t is a function of x. So capital X is function of x only, capital T is function of t only. So product of that two, so that we can write it as x into t, u is equal to x into t. So this you substitute in the given differential equation. So in place of u, here in place of u and here in place of u, we get dou by dou x of xt. So in this term, so t is constant, t you can write outside, so we get d t times d capital X by d small x is equal to, right hand side it is dou by dou t of xt. So again here x is constant, you can take outside, so we get 2x, and t is function of only small t, so that becomes ordinary derivative t capital T by d small t plus u is xt. So we get this. So then bring all x terms and t terms towards left and right hand sides. To do that, I'll just divide throughout by xt. So the left hand side becomes 1 by x d capital X by d small x, because t get cancels here. In right hand side, x get cancelled, so we get 2 by t d capital T by d small t, plus in the last term, so xt get cancelled, it is just 1. Now it is already in the form, so left hand side is function of x, right hand side is a function of t. So these two are equal. So this is equality is not possible always, unless until they are equal to same constant. That constant I have taken it as k. So therefore 1 by x d capital X by d small x is equal to 2 by t d capital T by d small t plus 1 is equal to k, will give rise to system of ODEs. So we get 1 by x d capital X by d small x is equal to k is 1 ODE, and 2 by t d capital T by d small t plus 1 is equal to k is the second ODE. You take this ODEs in separately and solve individually, then substitute back in u, will get the required solution. So I'll take each one. So first one is 1 by x d capital X by d small x is equal to k. So this separate the variables again. You can write d capital X by d capital X is equal to k times dx. So integrating this and rearranging, will get the solution for x is equal to a times e power kx. And similarly take second ODE and separate the variables, that is dt by d capital T is equal to k minus 1 by 2 into dt. Integrate this, we'll get integration of dt by t is log t is equal to k minus 1 by 2 is constant, integration of dt is t plus log b. So therefore taking log to other side, we'll get t is equal to b times e power k minus 1 by 2 into t. So this is a solution for t, and this is a solution for x. Substitute that in u is equal to xt. So we'll get u is x is a e power kx times t is b e power k minus 1 by 2 into t is equal to a into b, you rewrite it as capital C, it is again a constant, and exponential powers you just add, so we get e power k plus kx plus k minus 1 by 2 into t. So this is the complete solution. So where c is some arbitrary constant and k is any arbitrary constant. So we need to determine these two constants using the given condition here. So now I'll substitute that condition. So using the given condition, u is equal to 6 times e power minus 3x at t equal to 0. That means put t equal to 0 in this solution and use this u is equal to 6 times e power minus 3x. So I just substituted here u of x comma 0 is 6 e power minus 3x, and if I substitute here, this k minus 1 by 2 into t becomes 0, so we'll remain with e power kx. So 6 e power minus 3x is equal to c e power kx. So the comparing right hand side and left hand side and right hand side, will get c is equal to 6, that is coefficient of e power minus 3x and e power kx. So we'll get c value is 6. Similarly, e power minus 3x is equal to e power kx, that is exponential functions are equal, that is possible only if the powers are same. So using that, we'll get k is equal to minus 3, and substitute back this c and k values, will get u is 6 times e power minus 3x minus 2t is the required solution. This is the solution of the given PD.